We are starting to talk about exponential graphs. In this section, we'll cover exponential graphs. Logarithmic graphs come a little later. You should have seen these in Algebra 2. So now that we're in pre-calculus, we're going to take these. We're going to do just a little bit more with them. But today, we're going to talk about what makes something an exponential function. We're going to look at the basic features of the exponential graph, both decay and growth. And then we're going to look at what happens when you transform that graph. Finally, I'm going to give you a couple examples where we actually use the natural number. Graphing by hand, it can be a little bit tricky because E is irrational. So figuring out exactly where to place that. I mean, if you're using a calculator, you can find points pretty quickly. But if you just want to draw a sketch by hand, we'll do a couple of those so you can see how that works. As far as what makes an exponential function, I'll get right into it with my first example here, 4 to the x. What you see here is that we have a constant base, 4. The exponent is where the variable is. And that's what makes an exponential function. You have a constant, there can be a coefficient, you can have numbers added or subtracted after. But the only variable is in the exponent. That's what's going to produce your exponential graphs. So in this case, 4 to the x, if the base is bigger than 1, it makes what we call an exponential growth function. Now an exponential function, a base exponential function, I should say, is never going to cross the x-axis. We have a horizontal asymptote at the x-axis. In fact, if you make a little xy chart, you'll see what I mean. You can start with 0. 4 to the 0 power is 1. 4 to the first power is 4. 4 squared is 16. So this thing starts, once it starts growing, it grows really fast. Right up off the top of my page here. To the left, you get -1 would be 1/4. -2 would be 1/16. So it's going to get as small moving to the left as it gets big going to the right. So we've got the horizontal asymptote here on the left, and we have the unbounded growth here on the right. But this is why, oh, I missed those points. This is why we use exponential growth as an expression. It grows exponentially, they'll say. Although most of the time when people use it, they just mean grows really fast. They're not making a claim as to the nature of the growth, really, other than it's quick. But the difference between geometric and exponential growth is not something regular people care about. So here's my basic exponential graph. It's a little sloppy because I had to draw it twice. I missed the points. We've got the horizontal asymptote, which in the basic function is going to be at y equals 0. This graph, if you're just looking at it in a calculator and don't know what you're doing, you may be tempted to think that that's a vertical asymptote here on the right side. It is not. This graph will keep moving to the right. It's going to get very steep. So as you keep moving over to the right, it's going to get extremely tall. But it will keep going all the way to positive infinity. The limit as x approaches negative infinity for this particular function is 0. And the limit as x approaches positive infinity, which as I said, it will get there, is positive infinity. So this graph has very different behavior on either side. Let's see, 0, 1, and it has no x-intercepts. The y-intercept of the basic graph, when you're not multiplying by a coefficient out here, the basic graph will have a y-intercept of 1 because anything to the 0 power is 1. As we start transforming this graph, that point may move around. So not all exponential functions will go through 0, 1. But the basic ones do. This graph is always increasing. It has no turning points. It has no x-intercepts. It is continuous. You'll be analyzing several of these graphs on your homework. My second example for today is an exponential decay function. Now the two ways to spot exponential decay function are negative next to the x in the exponent. Although really, with what negative exponents mean, this can be expressed also as 1/5 to the x power. So you can spot an exponential growth function because it will either have a base bigger than 1 with a negative in front of the x in the exponent, or it will have a base that is less than 1 with no negative in the exponent. If you find yourself in a situation with a base that is less than 1 and a negative exponent, those are going to cancel because you should take the reciprocal. So you're actually going to end up with a growth function if you have both a base less than 1 and a negative in front of the x in the exponent. Whereas this example is a decay function. Its basic shape is the same, except that the asymptote is going to happen on the right, because as you continue to multiply by 1/5 repeatedly, the numbers are going to get smaller rather than bigger. And then it's going to head off to positive infinity as x approaches negative infinity. So the whole thing is just going to be backwards. So 0, 1 is the same. 1, instead of being 5, will be 1/5. And then, of course, 2 will be 1/25, which I can't even really draw. I'll just draw it really close there. Going to the left, -1, we'll flip this upside down, you'll get 5. And -2 would be 25, but there's no way I'm drawing that. So we have here, I'll try to actually get through my points this time, the same basic shape, but backwards. This is exponential decay. Note also no x-intercepts. The graph is always decreasing. It's continuous. And it has a horizontal asymptote, again at y = 0. Which is typical for the basic exponential function. As we start transforming it, the horizontal asymptote may move. So my third example involves a transformation. C of x, I'm going to do 1/2 to the power of x plus 1. Now those of you who were paying attention earlier this year will spot that plus 1 is right next to the x. That's on the inside of the function. So when we talk about transformations, we think in terms of h and k. In this case, h is -1. That's what changed this to a plus 1. It would be -1 if h were positive 1. So h here is -1. This is going to shift my graph one space to the left. So the point that used to be 0, 1, we're going to find is over here at -1, 1, which I will show you in a second. As far as fixing this graph so that you can draw it most efficiently, the first thing you want to do when getting ready to graph an exponential function is identify the horizontal asymptote. It's the most obvious feature. As long as there's no number being added on the outside, you don't need to worry about that. That can only shift if you shift up or down. A horizontal asymptote that you shift left and right doesn't actually change because it's already a horizontal line. It goes forever in both directions. So moving one space to the left isn't going to move that. It's only if you have a number added on the outside that the horizontal asymptote will change. So we're looking at y = 0 for our horizontal asymptote in this case. The next thing I recommend is at least 2 points. 3 might be better depending on how comfortable you are drawing these. But the easiest one to draw is always going to be the one that makes the exponent 0. So looking here, to make the exponent 0, I'm going to stick in -1. Now there's where the transformation comes into play, because depending on what h is, it's going to change what you want to stick in. So when I stick in -1, I will get an exponent of 0. Anything to the 0 power is 1. So there's my point that used to be the y-intercept, but has now been shifted to the left one because of this transformation. Now I'm going to stick in points. I'm going to stick in points nearby. Since this is 1/2, -2 is not a bad pick. That'll give me an exponent of -1, which means my answer will be 2. I can stick in -3, and I'll get 4. I can also stick in 0, and I will get 1/2. you stick in 1, you'll get an exponent of 2. 1/2 squared is 1/4, if you would like that one. I usually only require 2 points for these, although if you're graphing it on a graphing calculator, you may be comfortable copying the graph, finding fewer points. The more points you find, the more likely you are to get a nice looking graph. All right. D of x, my fourth example, has all kinds of transformations in it. X minus 4 plus 3. So as I said before, at the outset here, finding the horizontal asymptote is a good plan. I can see it already since I'm thinking about my transformation form here. The h is 4, the k is 3. That's going to move the graph up 3 spaces and to the right 4. So the whole thing's going to be shifted over, but also up 3, which moves my horizontal asymptote with it. So my horizontal asymptote is going to be at y. Have I been writing y equals 0 this whole time? Oh, that's right. Y equals 3. Good. Oh, I had a moment. I apologize for my moment. So y equals 3 is the horizontal asymptote. Now I need a couple points to put my graph in here. Again, I'm going to start with the one that makes the exponent 0. So 4. When I stick in 4, this becomes 2 to the 0, which is 1. Times 3 is 3, plus 3 is 6. 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. I need other points nearby. I can stick in 5, which will give me an exponent of 1. 6 plus 3 is 9. 7, 8, 9. So you can see there the function growing. Going in the other direction, I can stick in 3, and I'll get 3/2 plus 3. Since the exponent will be -1, this 2 will turn into 1/2. That's 4.5, 4.5. 1, 2, 3, 4.5. I can stick in 2. If you're still not comfortable drawing that, you can stick in more points. 2 to the -2nd power is 1/4, so that's 3/4 plus 3. 3 3/4 is about right there. I'm going to go ahead and draw it. I could do more, but that's 3.75. So it's coming across exponentially there. So there you have a transformation. Again, paying attention to our transformation notation can help you figure out which way it's been changed. But really, k is going to determine the horizontal asymptote, and then start by sticking in the values for x that will make the exponent 0 or close to 0. You're going to have a much easier time with the mental math. I'm going to skip e because we're doing natural number now, so I don't want e of x if I'm going to use a natural number in here. As promised, we're going to talk about using the natural number e in your graphs by hand. So here I've got e to the -x minus 1. As far as the basic shape of this graph, since e is about 2.7, this graph is a would-be growth, except that the exponent's negative. Right? The base is bigger than 1. The exponent's negative, so this is going to be a decay function. Because k is -1, I'm expecting a horizontal asymptote here at y equals -1. I need a couple of points. Making the exponent 0 is still my best bet. And the way I'm going to do that right now is by sticking in 0. So that gives me 1 minus 1, which is 0. I can stick in 1, but that's going to be a little tricky. So I'm going to stick in -1 instead. That'll give me e to the x. I know e to the x is e to the 1. E to the 1 is about 2.7. So when I subtract 1, I'm going to be about 1.7. So using 2.7 as sort of your estimate, and then strategically picking the values for x, that will make it easier to evaluate. negative 1, 1.7 is going to really help. Now 1 over x you can approximate at about 0.3. So when I subtract 1, I'm going to get negative 0.7. Again, that's a rough approximation, so it'll do for a little sketch. But if you need something more precise, you're probably going to want to use a graphing tool of some kind anyway, or a calculator. So this gives me plenty of points to sketch my exponential growth function. Now, as far as, well, let's move on to the next one then. So my last example for this section, 2e to the x plus 1 plus 2. First thing I'm going to do is note that it is exponential growth because the exponent no longer has a negative and e is bigger than 1. Also, the horizontal asymptote is here at y equals 2 because that's k. Because I'm familiar with transformations, this has been shifted to the left one as well, but it's also going to be twice as tall as a typical e to the x graph. Nevertheless, for my xy chart, I'm going to start with negative 1 because that'll make my exponent 0. E to the 0 is 1. That'll give me 2 plus 2, which is 4. I will then attempt to make the exponent 1 by sticking in 0. Now e is 2.7, so when I multiply that by, that gives me exponent of 1, which is 2.7 times 2 is 5.4, plus 2 is 7.4. 7.4 then is way up there, which is enough to go ahead and draw the curve. Although, as I said, you can use about 0.3 for e to the negative 1. So if I stick in negative 2 here, that's 2 times 0.3 is 0.6. So we're talking about somewhere around 2.6. And there's the graph. All right, well, that's sketching graphs of exponential functions, the basic ones, the transformed versions, and even the ones that involve e by hand. You can also, if you need more precision or want bigger numbers for some reason, I recommend a scientific calculator or a graphing calculator or some sort of graphing tool.